Hey guys, my name's Kennan Meyer, and today I'm going to be doing a presentation on the Markov's and Chebyshev's inequality. So, for Markov's inequality, we use it to answer the question, if we have a random variable x, we want to know what is the probability that the value of random variable x is far from its expectation. So, for Markov's inequality, it works for non-negative random variables, given that we have a random variable and its expectation. So those are the only two pieces of information you really need to construct a Markov inequality, which makes it very useful because you don't need that much knowledge about your random variable. You just need its x and its expectation. So let's look at the theorem. So Markov's inequality says that for a non-negative random variable x, with finite expected value, ex, and for any positive real number, a, that is greater than 0, the probability that x is greater than or equal to a is less than or equal to the expectation of x over a. And again, you can see that all we need is an x and its expectation to find the probability that x is greater than or equal to a. Okay, so that's Markov's inequality. Let's take a look at the proof. So consider we have a random variable that is 1 if x is greater than or equal to a, else it's 0. And if we sample all that when x is greater than or equal to a, we'll get 1 for that random variable. And if we say that x is non-negative, we can state that this random variable will always be less than or equal to x over a. And that makes sense because x is greater than or equal to a in this case. Therefore, the lowest it can be is 1 on the right side, and the left side is always 1. So the middle equation works. And if we just wrap the random variable's expectation, we can find that this is actually the probability that this random variable is 1, which turns out just depends if x is greater than or equal to a. So our expectation of our random variable will translates to the probability that x is greater than or equal to a, and we also have our expectation of x on the left-hand side to balance this out. So that leaves us with our Markov inequality. The probability that x is greater than or equal to a is less than or equal to the expectation of x over a. So let's take a look at using Markov's inequality in a problem, and we can see why it can be so useful at constructing a probabilistic upper bounds. So consider we have a bias coin which flips heads with probability 1/10 each time, and we flip this coin 200 times. So using Markov's inequality, we want to give an upper bound on the probability that it lands on heads at least 120 times. So this is a pretty straightforward problem. All we need is an x, which we have our bias coin, and we need our expectation of x. And our expected value of x is np. It's the number of times we're doing an action and the probability of an outcome. So we know that we land on heads with a probability of 1/10, and we're flipping a coin 200 times. So we can say that our expected value is 200 times 1/10, which is 20. So we can now construct a Markov inequality as shown below. We have our x, we have our expectation, and we have an a. So we can say that the probability of our bias coin landing on heads at least 120 times is less than or equal to the expectation of x over a, which is 20 over 120, which is a 1/6. So we have the probability that x lands on at least 120 times on heads is less than or equal to 1/6. So there's our probabilistic upper bounds for this problem. And it's very helpful. All we had to work with the problem was our expectation of x and a random variable. And we're able to construct some type of bounds on our probability. So that's the usefulness of Markov's inequality. However, since we're only using the expectation of x and x in this problem, you can kind of wonder how useful is Markov's inequality and how tight are these bounds that we're constructing for these random variables. So let's talk about flipping coins again. If we construct a Markov inequality for landing on heads or tails n amount of times, if we flip fair coins, so 50-50 chance, our Markov inequality gives us an upper bounds, a probabilistic upper bounds of roughly 1/2. But in reality, if we're flipping individual fair coins, we're getting 2 to the negative n is our upper bound. So in this case, our Markov's inequality is extremely wide when the actual problem is much more narrow. So in this case, Markov's inequality isn't that useful. And but when is it useful? So again, let's talk about flipping coins. What if we glued all our coins together and we flipped them? Therefore, we all get heads or we all get tails. So if we use Markov's inequality, we get the same upper bounds, 1/2. And in reality, our upper bounds really is 1/2. So in this scenario, our Markov inequality gave us a very tight upper bounds. And this kind of makes sense, because if we flip a bunch of fair coins, our outcome is going to be mostly distributed around that 50-50 outcome that we expect. And that the results, based on the expectations, don't really vary that much. It's very rare to get all heads or all tails if you're flipping individual coins. And that's kind of an outlier. So our Markov inequality is constructing a bounds with that in mind, because it's part of our expectation that we could get all heads or all tails. So it's very wide. When in reality, it's really not, the results aren't that wide for the fair coins. But if we think about the glued coins, we have very wide results. We have either all heads or all tails. That's as wide as you can get when you flip coins. Therefore, our Markov inequality we set up for this actually is very tight, because it is the actual results are very wide, and so is the Markov inequality. So we can kind of see when Markov's inequality is more useful and when it's not. So if we wanted to improve on Markov's inequality, perhaps we can give it more information to construct a better bounds. And this is Chebyshev's inequality. It's a special case of Markov's inequality that not only allows for any random variables, not just non-negative like Markov's inequality, but in theory it constructs a tighter bound because you give it more information. Chebyshev's inequalities theorem is such: for a random variable x with finite expected value ex and finite non-zero variance, and for any real number a that is greater than 0, we can say that the probability that the absolute value of x minus ex is greater than or equal to a is less than the variance over a squared. So we can see this is very similar to Markov's inequality, just structure-wise, and we'll see in the proof that it's actually derived from Markov's inequality, because it is a special case, and we end up getting variance from it. So in theory, Chebyshev's gives a more tighter bounds, because you're not just giving it ex with x, you're also giving it a variance. So with this extra knowledge, you should be able to construct a better, tighter, probabilistic upper bounds on your problem, a random variable. So let's take a look at the proof. It's a bit more complicated than Markov's inequality, but it's really not that bad. If we take the left-hand side of Markov's inequality, so the probability that x is greater than or equal to a, and instead we substitute in the absolute value of x minus ex as x, we have this first equation, and if we just square the inequality on both sides, it's the same probability. So that's our setup. And if we make this into a Markov inequality, we get our middle equation. So we can see that in this case, x is still the absolute value of x minus ex. And on the upper right-hand side, we just take that expectation of x. And in this case, we're using the squared version, so a is squared and same as x minus ex. So this is a valid Markov inequality. And again, if we take a look at the top right-hand side of that middle equation, it turns out this is the definition of variance, the expectation that x minus ex squared. So we can finish up our Chebyshev's inequality proof by simplifying that to variance. And there you have it. We have the probability that the absolute value of x minus ex is greater than or equal to a is less than or equal to variance over a squared. And we can see that it's, again, derived from a Markov inequality. And this is just describing the proof. So let's talk about applications of cryptography real quickly. So we can see that both these inequalities revolve around creating probabilistic upper bounds. Markov's inequality only requires an expectation for a random variable, so we can calculate these upper bounds without studying the random variable that much. You don't need that much knowledge to construct these probabilistic upper bounds. So if we have a random variable that we don't know much about, we can still calculate upper bounds, and this has tons of application in cryptography. We've seen this many times in our class, such as running a distinguisher, proving perfect security or secrecy and correctness. And for Chebyshevs, since it's an improvement on Markov's, given that you have a variance and therefore more knowledge about your random variable, you can use it in place of Markov's to give a better, tighter bound. So any application in cryptography where Markov's inequality is used, if you have variance, you can use Chebyshevs. Another specific area Chebyshevs is useful in is the analysis of error probability of approximation, and that's for repeated sampling. Was a particular area where Chebyshevs is always used. In general, these both are considered very basic probabilistic upper bounds inequalities, and there are many more complicated concepts that relate to these, but they use Markov's and Chebyshevs as a base. I think another presentation is Chernoff bounds, and that again uses Chebyshevs inequality as a basis. But yeah, overall, both these inequalities can be constructed without a lot of information, and they give you a good, reasonable probabilistic upper bounds on a random variable.